Hello and welcome. My name is Alan, and today we're back with more ideas and opinions of Albert Einstein. We're still reading this Physics and Reality. Today we'll be reading part 2, Mechanics and the attempts to base all physics upon it. An important property of our sense experiences and more generally, of all of our experiences is their temporal order. This kind of order leads to the mental conception of a subjective time, an ordering scheme for our experience. The subjective time leads then via the concept of the bodily object and of space to the concept of the objective time, as we shall see later on. Ahead of the notion of objective time, there is, however, the concept of space, and ahead of the latter, we find the concept of the bodily object. The latter is directly connected with complexes of sense experiences. It has been pointed out that one property which is characteristic of the notion bodily object is the property which provides that we coordinate to it in existence, independent of subjective time and independent of the fact that it is perceived by our senses. We do this in spite of the fact that we perceive temporal alterations in it. Poincaré has justly emphasized the fact that we distinguish two kinds of alterations of the bodily object: changes of state and changes of position. The latter, he remarked, are alterations which we can reverse by voluntary motions of our bodies. That there are bodily objects to which we have to ascribe within a certain sphere of perception no alteration of state, but only alterations of position, is a fact fundamental importance for the formation of the concept of space in a certain degree, even for the justification of the notion of the bodily object itself. Let us call such an object practically rigid. If, as the object of our perception, we consider simultaneously, i.e., as a single unit, two practically rigid bodies, then there exist for this ensemble such alterations as cannot possibly be considered as changes of position of the whole, notwithstanding the fact that this is the case for each one of the two constituents. This leads to the notion of change of relative position of the two objects, and in this way also the notion of relative position of the two objects. It is found, moreover, that among the relative positions there is one of a specific kind which we designate as contact. Permanent contact of two bodies in three or more points means that they are united to bodies to a quasi-rigid compound body. It is permissible to say that the second body forms then a quasi-rigid continuation of the first body and may, in its turn, be continued quasi-rigidly. The possibility of the quasi-rigid continuation of a body is unlimited. The totality of all conceivable quasi-rigid continuations of a body, b to the zero power, is the infinite space determined by it. In my opinion, the fact that every bodily object situated in any arbitrary manner can be put into contact with the quasi-rigid continuation of some given body B0, body of reference, this fact is the empirical basis of our conception of space. In pre-scientific thinking, the solid Earth's crust plays a role of B0 and its continuation. The very name geometry indicates that the concept of space is psychologically connected with the Earth as an ever-present body of reference. The bold notion of space, which preceded all scientific geometry, transformed our mental concept of the relations of positions of bodily objects into the notion of the position of these bodily objects in space. This, of itself, represents a great formal simplification. Through this concept of space, one reaches, moreover, an attitude in which any description of position is implicitly a description of contact. The statement that a point of a bodily object is located at a point P of space means that the object touches the point P of the standard body of reference B0, supposed appropriately continued at the point considered. In the geometry of the Greeks, space plays only a qualitative role, since the position of the bodies in relation to space is considered as given. It is true, but is not described by means of numbers. Descartes was the first to introduce this method. In his language, the whole content of Euclidean geometry can axiomatically be founded upon the following statements. 1. Two specified points of a rigid body determined by a segment. 2. We may associate multiples of numbers x1, x2, x3 to points of space in such a manner that for every segment p something power minus p to the nth power under consideration, the coordinates of whose endpoints are x1 squared, x2 squared, x3 squared, actually I think that's to the t is what it is, x1 to the n power, x2 to the n power, x3 to the n power. The expression s squared equals x1 to the n power minus x1 to the r power squared plus x2 n power minus x2 r power squared plus x3 n power minus x3 r power squared as independent of the position of the body and of the positions of any and all other bodies. The positive number s is called the length of the segment, or the distance between 2 points PR and PN of space, which are coincident with the points PR and PN of the segment. The formulation is chosen intentionally in such a way that it expresses clearly not only the logical and axiomatic, but also the empirical content of Euclidean geometry. The purely logical, axiomatic representation of Euclidean geometry has, it is true, the advantage of greater simplicity and clarity. It pays for this, however, by renouncing a representation of the connection between the conceptual construction and the sense experiences, upon which connection alone the significance of geometry for physics rests. The fatal error that logical necessity preceding all experience was the basis of Euclidean geometry and the concept of space belonging to it. This fatal error arose from the fact that the empirical basis on which the axiomatic construction of Euclidean geometry rests had fallen into oblivion. Insofar as we can speak of the existence of rigid bodies in nature, Euclidean geometry is a physical science which must be confirmed by sense experiences. It concerns the totality of laws which must hold for the relative positions of rigid bodies independently of time. As one may see, the physical notion of space, also as originally used in physics, is tied to the existence of rigid bodies. From the physicist's point of view, the central importance of Euclidean geometry rests in the fact that the laws are independent of the specific nature of the bodies whose relative positions it discusses. Its formal simplicity is characterized by the properties of homogeneity and isotropy and the existence of similar entities. The concept of space is, it is true, useful, but not indispensable for geometry proper, i.e., the formation of rules about the relative positions of rigid bodies. By contrast, the concept of objective time, without which the formulation of the fundamentals of classical mechanics is possible, is linked with the concept of the spatial continuum. The introduction of objective time involves two postulates which are independent of each other. One, the introduction of the objective local time by connecting the temporal sequence of experiences with the readings of a clock, i.e., of a periodically recurring closed system. And two, the introduction of the notion of objective time for the events in the whole space, by which notion alone the idea of local time is extended to the idea of time in physics. Note concerning one, as I see it, it does not mean a petitio principii if one puts the concept of periodical recurrence ahead of the concept of time, while one is concerned with the clarification of the origin and the empirical content of the concept of time. Such a conception corresponds exactly to the procedure of the concept of the rigid or quasi-rigid body in the interpretation of the concept of space. Further discussion of two, the illusion which prevailed prior to the enunciation of the theory of relativity, that from the point of view of the experience, the meaning of simultaneity in relation to the spatially distant events, and consequently that the meaning of physical time is a priori clear. This illusion had its origin in the fact that in our everyday experience we can neglect the time of propagation of light. We are accustomed on this account to fail to differentiate between simultaneously seen and simultaneously happening. And as a result, the difference between time and local time is blurred. The lack of definition or definiteness, which, from the point of view of its empirical significance, adheres to the notion of time in classical mechanics, was veiled by the axiomatic representation of space and time as given independently of our sense experiences. Such a use of notions, independent of the empirical basis to which they owe their existence, does not necessarily damage science. One may, however, easily be led into the error of believing that these notions, whose origin is forgotten, are logically necessary and therefore unalterable, and this error may constitute a serious danger to the progress of science. It was fortunate for the development of mechanics and hence also for the development of physics in general that the lack of definiteness in the concept of objective time remained hidden from the earlier philosophers as regards its empirical interpretation. Full of confidence in the real meaning of the space-time construction, they developed the foundation of mechanics, which we shall characterize schematically as follows. A. Concept of a material point, a bodily object which, as regards its position and motion, can be described with sufficient accuracy as a point with coordinates x1, x2, x3. Description of its motion in relation to the space BO by giving x1, x2, x3 as functions of the time. B. Law of inertia. The disappearance of the components of acceleration for a material point which is sufficiently far away from all other points. C. Law of motion. For the material point, force equals mass times acceleration. D. Laws of force interactions between material points. In this, B is merely an important special case of C. A real theory exists only when the laws of force are given. The forces must, in the first place, only obey the law of equality of action and reaction in order that a system of points permanently connected to each other by forces may behave like one material point. These fundamental laws, together with Newton's law for the gravitational force, form a basis of the mechanics of celestial bodies. In this mechanics of Newton, and in contrast to the above conceptions of space derived from rigid bodies, the space BO enters in a form which contains a new idea. It is not for every BO that validity is asserted for a given law of force for B and C, but only for BO in an appropriate state of motion, inertial system. On account of this fact, the coordinate space acquired an independent physical property which is not contained in the purely geometrical notion of space, a circumstance which gave Newton considerable food for thought. Pell experiment. Classical mechanics is only a general scheme. It becomes a theory only by explicit indication of the force law, D, as was done so very successfully by Newton for celestial mechanics. From the point of view of the aim of the greatest logical simplicity of the foundations, this theoretical method is deficient insofar as the laws of force cannot be obtained by logical and normal considerations, so that their choice is a priori to a large extent arbitrary. Also, Newton's law of gravitation is distinguished from the other conceivable laws of force exclusively by its success, in spite of the fact that today we know positively that classical mechanics fails in a foundation dominating all physics. It still occupies the center of all our thinking in physics. The reason for this lies in the fact that, regardless of important progress reached since the time of Newton, we have not yet arrived at a new foundation of physics concerning which we may be certain that a manifold of all investigated phenomena and of successful partial theoretical systems could be deduced logically from it. In the following lines, I shall try to describe briefly how the matter stands. First, we try to get clearly in our minds how far the system of classical mechanics has shown itself adequate to serve as a basis for the whole of physics. Since we are dealing here only with the foundations of physics and with its development, we need not concern ourselves with the purely formal progresses of mechanics, equations of Lagrange, canonical equations, etc. One remark, however, appears indispensable. The notion material point is fundamental for mechanics. If now we seek to develop the mechanics of a bodily object which itself cannot be treated as a material point, and strictly speaking, every object perceptible to our senses is of this category, then the question arises, how shall we imagine the object to be built up out of the material points, and what forces must we assume as acting between them? The formulation of this question is indispensable of mechanics if mechanics is to pretend to describe the object completely. It is in line with the natural tendency of mechanics to assume these material points and the laws of forces acting between them as invariable, since temporal changes would lie outside the scope of mechanical explanation. From this, we can see that the classical mechanics must lead us to an atomistic construction of matter. We now realize with special clarity how much in error are those theorists who believe that the theory comes inductively from experience. Even the great Newton could not free himself from this error, hypothesis non fingo. In order to save itself from becoming hopelessly lost in this line of thought, atomism, science proceeded first to the following manner. The mechanics of a system is determined by its potential energy, is given as a function of its configuration. Now, if the acting forces are on such a kind as to guarantee the maintenance of certain structural properties of the systems configuration, then the configuration may be described with sufficient accuracy by a relatively small number of configuration variables, QR. The potential energy is considered only insofar as it is dependent upon these variables. For instance, description of the configuration of a practically rigid body by 6 variables. A second method of application of mechanics, which avoids the consideration of a subdivision of matter down to real material points, is the mechanics of so-called continuous media. The mechanics is characterized by the action that the density and the velocity of matter depend continuously upon coordinates and time, and that the part of the interactions not explicitly given can be considered as surface forces, pressure forces, which again are continuous functions of position. Herein we find the hydrodynamic theory and the theory of elasticity of solid bodies. These theories avoid the explicit introduction of material points by fictions which, in the light of the foundation of classical mechanics, can only have an approximate significance. In addition to their great practical significance, these categories of science have, by developing new mathematical concepts, created those formal tools, partial differential equations, which have been necessary for the subsequent attempts at a new foundation of all of physics. These two modes of application of mechanics belong to the so-called phenomenological physics. It is characteristic of this kind of physics that it makes as much use as possible of concepts which are close to experience, but for this reason has to give up, to a large extent, unity in the foundations. Heat, electricity, and light are described by separate variables of state and material constants other than the mechanical quantities. And to determine all of these variables in their mutual and temporal dependence was a task which, in the main, could only be solved empirically. Many contemporaries of Maxwell saw in such a manner of presentation the ultimate aim of physics, which they thought would be obtained purely inductively from experiences on account of the relative closeness of the concepts used to experience. From the point of view of the theories of knowledge, St. Mill and E. Mach took their stand approximately on this ground. In my view, the great achievement of Newton's mechanics lies in the fact that the consistent application has led beyond the phenomenological point of view, particularly in the field of heat phenomena. This occurred in the kinetic theory of gases and statistical mechanics in general. The former connected the equation of state and of the idea gases, viscosity, diffusion, and heat conductivity of gases and radiometric phenomena of gases, and gave the logical connection of phenomena which, from the point of view of direct experience, had nothing whatever to do with one another. The latter gave a mechanical interpretation of the thermodynamic ideas and laws and led to the discovery of the limit of applicability of the notions and laws of the classical theory of heat. This kinetic theory, which by far surpassed phenomenological physics as regards the logical unity of its foundations, produced, moreover, definite values of the true magnitudes of atoms and the molecules which resulted from several independent methods and were thus placed beyond the realm of reasonable doubt. These decisive progresses were paid for by the coordination of atomistic entities to the material points, the constructively speculative character of these entities being obvious. Nobody could hope ever to perceive directly an atom. Laws concerning variables connected more directly with experimental facts, for example, temperature, pressure, speed, were deduced from the fundamental ideas by means and complicated calculations. In this manner, physics, at least part of it, originally more phenomenologically constructed, was reduced by being founded upon Newton's mechanics for atoms and molecules to a basis further removed from direct experiment, but more uniform in character. Now, let's go back and go over some of the notes they have at the bottom of the page here. Early on, they go, it is found, moreover, that among the relative positions there is one of a specific kind which we designate as contact. And at the bottom here it says, it is the nature of things that we are able to talk about these objects only by means of concepts of our own creation, concepts which themselves are not subject to definition. It is essential, however, that we make use only of such concepts concerning the coordination to our experience, we feel no doubt. A little further in, we have on account of the fact the coordinate space acquired an independent physical property which is not contained in the purely geometrical notion of space, a circumstance which gave Newton's considerable food for thought, the Pell experiment. And at the bottom it reads, this defect of theory could only be eliminated by such a formulation of mechanics as would claim validity for all BO. This is one of the steps which led to the general theory of relativity. A second defect, also eliminated only by the introduction of the general theory of relativity, lies in the fact that there is no reason given by mechanics itself for the equality of the gravitational and inertial mass of the material point. We also have even the great things Newton could not free himself from this error, hypotheses non bingo. At the bottom it reads, I make no hypotheses. So yeah, Einstein looking at physics and how we've had to do a lot of it by deduction and thought rather than just simple experience and physical and empirical data. He also shows how Newton played the part as being one of the fathers of physics and how we found to make the changes needed. But anyway, I'm going to go ahead and end that here. It's already been about 35 minutes. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.